today's bootcamp, which is on electrochemistry foundation for next-gen batteries from AA to charge transfer kinetics. I welcome Manjunath sir, who is a PhD holder who has well-versed knowledge in this particular domain, and he has published variety of papers on these topics, and he is the main pillar on the course we have launched. I welcome you, sir.
Oh, thanks, Vinayak. Good evening, everyone. Myself,
Over to
Dr.
you, sir.
Manjunath. I'm a researcher in material chemistry, and it's a pleasure to welcome you all to this online bootcamp on electrochemistry foundations for lithium-ion batteries, which are used in EVs. So we will explore in the next 1 hour. We'll explore from fundamentals double layer to charge transfer kinetics, which plays a vital role in the battery battery efficiency. So in this 1 hour of this bootcamp, I'll just briefly introducing about the relevance to EVs and lithium-ion batteries. Then I'll just discuss about the lithium battery working mechanism by taking lithium cobalt oxide as an example. So from then I'll shift to how the voltage and capacity of the battery, what are the characteristics, what are the factors on which this voltage and capacity is defined, and how the materials are being chosen in order to optimize voltage and capacity. So then I'll introduce you to the voltage EMF and the Nernst equation. So then we are going to discuss about very important concept that is called over potentials, and under that we discuss mass transfer based on Nernst Planck equation and charge transfer over potential that is based on Butler-Omer equations. So these are the fundamental concepts which needs to be understood of those who are in this field, especially working in battery. So finally, I'll summarize about the things that I'll be discussing. So to the global transition. So we know that the 21st century marks a shift from fossil fuel engines to the electrochemical energy system. So we can see that the present electrical vehicle revolution, it symbolizes this transformation, because they're very much sustainable, not like the fossil fuels are not eco-friendly and sustainable. And this electrochemical energy system powered vehicles are more sustainable, efficient, and digitally intelligent. So we know that the major OEMs like Tesla, Tata, Hyundai, BYD, and Toyota are investing heavily in this battery innovation. So we also over 20% of all new cars sold globally in 2024 were electric vehicles. It is about more than 17 million units. And among this, China is taking the lead. China has led EV sales with approximately 60% of 17 million units in the global market. And Europe is contributed about more than 25%, and the United States is around 10%. And currently, in the last 2024 data reveals that the average global battery cost, it is dropped to $115 per kilowatt, and with China having the lowest regional cost, that is about $94 per kilowatt. So the battery prices in Europe and US were respectively 31% and 48% higher than China. So India also playing a vital role. So India's major EV clusters, especially in Bangalore, Pune, Chennai, accounted for about 60% of national EV manufacturing and infrastructure. So with this background, let us move to the battery systems. So we know that the battery is a electrochemical reactor that converts chemical energy into electrical energy through redox reactions. So which has important components like cathode, anode, and electrolyte, separator, and current collectors. So it's made up of various components so that we come across in my previous bootcamp. So I have covered about the materials used in all this cathode, anode, electrolyte, separator, and current collectors, their characteristics, their structure, and the crystal chemistry has been detailed. And in EVs, we use lithium-ion batteries because it has very high energy density, about 250 to 300 watt-hour per kg, long cycle life, and reversible intercalation chemistry. It's not like other ions. Lithium is the smallest ion. The intercalation and deintercalation, that to reversible, is possible in this technology. So performance and safety depend on interfacial reactions, ion transport, charge transfer. So all governed by these electrochemical principles. Hence, the deep understanding of battery chemistry is very much essential for innovation across materials, design, and control. And then it can effectively power electric vehicles. So the main principle behind this is electrochemistry, which explains how the electrons and ions move in between the anode and cathode. So for example, if you take lithium-ion battery, electrons are during the charging. So electrons are moving from cathode to anode externally, and lithium ions moving from cathode to anode, and vice versa during discharging. So the determining key properties are the cell voltage from electrode potentials and current response. This is from charge transfer kinetics. I'll be covering the Butler-Romer equations, and losses from ohmic and mass transfer over potential. So mastering electrochemistry means understanding why real batteries deviate from real thermodynamics. So to design the better EV batteries, we must connect materials in the sense the electrode materials, cathode, anode is graphite, cathode if you take LFP or NMC materials, and their interfaces, because they're all sandwiched one above other. The anode, then we have a separator, and the cathode. The interface chemistry plays a vital role, and the reactions through these electrochemical models. So in this today's session, I cover how voltage arises. So by taking the Nernst equation, and then why voltage drops. So I'll introduce you to overpotential, then how the fast the reactions in battery happens. So that is based on Butler-Romer kinetics. So these are the electrochemical foundations behind every lithium-ion cell used in modern EVs. So we know that the battery cells, based on the design, they have classified into cylindrical cell, hard prismatic, and soft prismatic, that is pouch cell. Their arrangement, the electrode inside, they are different. Physically, they are different, but the electrochemistry of all these formats are same. Whatever may be the shape, but most of the electrochemistry is same for that. So let us understand the battery chemistry by taking lithium cobalt oxide, which was the first rechargeable battery, which was really proposed by Professor Goodenough, the Nobel Prize winner in this technology. So this lithium cobalt oxide battery we can find in all our laptops and mobile phones. So this battery consists of lithium cobalt oxide as cathode. So the question arises, why we are behind lithium? Because lithium metal, among all the metals, lithium is the lightest metal and the first metal. In the periodic table, if you look at, the first element is hydrogen, and the next element is helium, and then lithium. So this is the first metal, and it is having very low reduction potential value. Very low reduction potential value means it is having very high oxidation tendency, means it can give away the electron easily compared to all other elements. So because of that, it provides very high voltage and high power density, because the weight of this metal ion is very small, because this is the first lightest metal among all the other metals. So and, since it is the smallest ion, it can be easily stored in the metal oxide matrices, crystal structures that I have discussed in my previous bootcamp, that is tetrahedral and octahedral voids. This lithium ion can be easily intercalated in the layered cathodes. So this lithium cobalt oxide battery, as I mentioned, the battery is consisting of anode, cathode, electrolyte, separator, etc. So this battery is actually the anode part is coated with copper. That is, the copper is a current collector, a thin film, and it is coated with a graphite powder, and it is represented by C6. So copper foil on which the graphite powder is made in the form of slurry, and then it is being coated and then dried. It's just a graphite and some binder coated on copper foil. So then the cathode. So the cathode chemistry, we use the lithium cobalt oxide. It is also called LCO material, which is the layered oxide. Layered oxide means the one layer we have lithium, another layer we have cobalt and oxygen. This black color powder, the lithium cobalt oxide powder, is mixed with a binder and some conducting fillers like Super P, and then dissolved in a slurry, some NMP solvent, and then coated on aluminum foil. So aluminum foil acts as a current collector for cathode, and copper foil acts as a current collector for the anode. So then both are dried, and then these two are separated by a separator. This is the third film, which is basically made up of polyethylene or polypropylene, the polymer separator. So it's actually porous in nature. It is electrically insulating. It allows only the ions to move between the anode and cathode. Okay, and then we fill the electrolyte. So lithium ion battery, we generally use non-aqueous. Non-aqueous means which is free from moisture or water. So water-based electrolytes are not recommended because lithium is violently reacting with chemically reacting with water. So therefore, only the non-aqueous electrolytes like ethyl or methyl carbonate, some organic solvents which are chemically stable with respect to the lithium, containing the salts of lithium, so that to increase their ionic conductivity. So this is actually liquid. So this is the solution. This is a thin film, and this is thin film, and this is thin film. Anode, cathode, and separator, all the three are thin film, and the electrolyte is a liquid, a solution containing organic solvent and the lithium salts. So it is filled, and then it is sealed. In my previous bootcamp, I have explained about the manufacturing and the fabrication of this. Those who are interested can go back and click that link to get some glimpse about the manufacturing of the cell. So once we are packed with this, so let us understand the chemistry and the electrochemistry inside of this cell. So this is a representation of this lithium-ion battery, and assume that this is a copper current collector coated with graphite. So graphite is actually just representing in the form of structure, external structure. Just to show you, it is layered structure. You can see that this is actually graphite. We all know that it is a layered structure. Means in between we have enough space. Between the two layers, we have enough space so that the lithium ion can intercalate here. So then on the right hand side, we have aluminum current collector coated with lithium cobalt oxide cathode material. So similar, the construction is everything, the mechanism is same for even NMC battery and LFP battery, which are used in EVs. Only the materials are different. Okay, so lithium cobalt oxide, you can see that it is a layered oxide. So this is the cobalt oxide, then we have lithium oxide layer, this one, and then cobalt oxide. So these intercalated lithium ions can be removed and then filled back by charging and by discharging. And this is the anode, and this part is the cathode film, and these two are separated by another thin film that is called separator. It is porous in nature. So the porosity is very much important because when we charge the battery, so the lithium ion, this cobalt undergoes oxidation here. Cobalt will be in +3 oxidation state, and it goes to cobalt +4 oxidation state by releasing electron. So this electron is pushed through this external wire. It is charged by connecting to DC source. So electrons are removed from this and then pushed to graphite. Graphite becomes negatively charged and this becomes positively charged. As a result of that, the voltage increases. So the positive charge increases and the negative charge increases at anode. Since the negative charge increases, then that lithium ions started moving towards graphite. And there the lithium ion combines with that electron and forms metallic lithium, and it exists between the layers of the graphite. So both lithium ion and lithium atom, the size is almost smaller than the distance between the two layers. The distance between the two layers of graphite is about 0.335 nanometer, and you can see the lithium ion is about 0.076 nanometer, and lithium atom is 0.155 nanometer. That's my size, very small. They can be easily filled in with graphite. Let us look at the reactions. So the mechanism of this. So we know that the anode, the copper is actually coated with graphite, and at cathode, the aluminum is coated with lithium cobalt oxide. When we start charging, this is the cathode, right? And this is the anode. So electrons are pushed. So this cobalt, LiCO2 cobalt, is in +3 oxidation state. This undergoes oxidation to give X electron, and it becomes +4. So if you remove X electron, X cobalt loses X electron from +3 to, and they'll go to +4 oxidation state. And at the same time, the same quantity of the lithium ions are being deintercalated from that lithium cobalt oxide matrix. So this electrons are made to push to the anode externally through wire, and the lithium ion is made to push. They started moving towards anode through solution. So then these two, they will enter here. Okay, the graphite. So the graphite combines with lithium and this electron, and here lithium intercalates inside the graphite, that is represented by LiXC6. So the overall reaction here is we have the cathode material LiCO2 coated on aluminum, and we have a carbon graphite coated on copper. So here this will give electron externally, and internally lithium. If you remove one electron, means one lithium ion will go to graphite. If you push 10 electrons, 10 lithium ion are pushed to graphite. So it is represented by X electrons are removed, X lithium ions are being pushed to graphite. So the state of charge depends on the amount of depends on X. So if X is more, SOC is more, the state of charge is more. So those electrons are being removed from the cobalt +3. So therefore, X number of cobalt undergo oxidation. They remain in the +3 oxidation state. So this is the overall reaction that is expected in cobalt oxide battery. Similarly, even if you take NMC or LFP, the graphite is common. This reaction is common since we use graphite as anode for both NMC and LFP battery. Once we charge the battery, the voltage increases because we are removing electron from the cathode, and cathode is becoming more positive and anode is becoming more negative. So once it is being charged, the voltage increases. The SOC may increase to 100%. Then the battery start discharging spontaneously. So this is non-spontaneous. This is non-spontaneous. It means it is at the cost of the energy. Here we are supplying energy from outside. Here we are supplying electrical energy and make chemical reactions to happen inside. Here already the battery is active, the energy is stored, then the chemical energy is getting converted spontaneously to electrical energy. So this is spontaneous reaction. So we call, during discharging, it acts as a galvanic cell. Galvanic cell. Okay. So you can see now during charged, after charging, the anode is rich in lithium, LiFC6. So, and the cathode is deficient in lithium, and as well as the electrons, cobalt plus 4 oxidation state. So they want that lithium and electron back. So therefore, so that lithium rich graphite start undergoing oxidation. So oxidation means it releases electron, and these electrons are spontaneously they're coming out externally through that external wire, and that results in the electrical energy. Okay. And the lithium ions have started moving back and enters to that lithium cobalt oxide. So they will go back to their original place and finally get back the same compound. You can see here we have started with LiCO2 and charging, and after discharging we are getting back that LiCO2. So this is called one cycle. So this is called one cycle. So like that, again we go for charging and discharging, and we can expect 1,000, 2,000, and 3,000 cycle. That depends on the battery chemistry. So upon charging and using for several cycles, because of the structural damage inside the cell, the voltage, the expected voltage cannot be achieved. It may drops down with the usage of the battery. So let us understand the electrochemistry, the principles, how those electrochemistry principles helps us to understand this mechanism and the rate of the reaction, the rate of the electron charge transfer. So here the electrons are transferring, that is called charge transfer, and the lithium ion is moving between anode and cathode, like shuttling between anode and cathode through the solution. So there is a transfer of the ion and there is a transfer of the electron. So the two different medium in the solution. So it has to experience a lot of resistances. The lithium ion has to come out from the cathode, that too from solid matrix, so that the resistance experienced by that lithium when it is coming out from the solid matrix is different. Then once it enters into the electrolyte, that resistance is different. Then it has to pass through the separator, then it will enter into the graphite. So it has to experience various resistances. As a result of that, the voltage drops, and we call it as a over potential. So I'll be touching those concepts in my future slides. Let us understand the voltage. So the voltage is the difference between the anode and cathode nature. So it is represented by the Nernst equation. Nernst equation is the E is equal to E naught, the cell voltage. This is the standard electrode potential, cell potential, minus RT by NF into log base E. So the activity of the species, reduced species, and the activity of oxidized species. So generally the Nernst equation is defined for OX means oxidized species, accepts electron, and it forms reduced species, or some report like this. This is also correct. Both are same. O means oxidized, means there already electrons are being removed. R means they can donate electron. So it is more commonly, it is represented by Q. So the reaction E, this is for E cell is equal to E naught cell minus RT by NF into log Q. So where E cell is the cell potential under non-standard conditions. This is non-standard conditions, other normal conditions. And this is under standard conditions, 25 degree centigrade and 1 atmospheric conditions, those conditions, and 1 molar concentration of the ions. R is a gas constant, we know that, and T is the temperature, N is the number of electrons being transferred. In case of lithium battery chemistry, N is always taken as 1 because lithium can give or accept 1 electron. F is a Faraday's constant, and Q is the reaction quotient. It's a product by reactant, means reduced species divided by oxidized species. So with respect to the battery, that lithium cobalt oxide graphite cell, the Nernst equation to define, let us write the reaction now. So LiCOO2. So this is the cathode material, and this is anode graphite. So anode. So when you charge, they are getting converted to lithium deficient cobalt oxide and lithium rich graphite. Overall, the cell reaction involves lithium ion movement between the two electrodes. So, okay. So this is the cathodic reaction during charging. This is during charging. So after we construct the cell now, generally the anode, the graphite is pure graphite. There will not be any lithium. And the cathode is pure lithium cobalt oxide. So then we go for charging. During charging, we remove lithium from the cathode and electron from the cathode, lithium cobalt oxide. Anode, we push them to the graphite. So this is what I have explained. If you write the Nernst equation for this, the LiCOO2, this is LiCOO2 and graphite cell. The voltage, it is also called voltage or EMF, or driving force, electromotive force, is equal to E naught of cathode. So E naught of cathode minus E naught of anode. E naught of cathode means that is LiCOO2, and E naught of anode, that is graphite, minus RT by NF into log base E to the activity, the concentration of lithium ion in the cathode divided by the concentration of lithium ion in the anode. Okay. Initially, the voltage is less because the concentration of lithium is higher. Okay, the concentration of lithium is high, and this is nil or zero. So therefore, this will be very less. When you charge, when you start charging, what happens? This concentration decreases because we are pushing the lithium ion to anode, right? This concentration increases. So this concentration decreases and this concentration increases. So overall, this term decreases, and this will decrease. Since this will decrease, so E cell minus E naught cell increases. So the voltage increases. So as lithium ion concentration changes during charge and discharge, the cell voltage also changes. So here the cell voltage is mainly depending on the lithium ion concentration in the anode and cathode. So these two remain constant, actually, the E naughts. So this E cell, which directly explains about the open circuit voltage, it is called OCV. It is a function of SOC, state of charge. So, and the voltage drop at low state of charge, this is due to the concentration changes and internal resistances. So that I'll discuss in the later slide. Flat region, this is because of equilibrium state attains between the anode and cathode. Okay. So if you next let us understand with respect to the battery, the cell voltage with respect to the various battery chemistries. So the NMC battery, it is they call it as high voltage battery, and the LFP battery is 3.2 low voltage. So here the NMC means graphite is anode and NMC is cathode. Here also graphite is anode and NMC is cathode. So this is anode and this is cathode, anode and cathode. So the cell voltage for NMC is high and LFP is less. So let us understand why. So what is the chemistry that makes the cell voltage for NMC high and the cell voltage for LFP low, 3.2 volts? So we know that the theoretical voltage is the difference between the electrical potential of cathode and the anode in batteries. That's called battery voltage. So it is actually it's determined by the compatibility of the whole system. If you look at this energy level diagram of the components used in the battery, generally to construct any battery, the anode, the chemical potential of the anode should be very high. So this is the chemical potential of anode. The energy of that should be high, because what is the nature of the anode? The anode nature is that it should donate electron, right? It should donate electron spontaneously. If it has to donate electron spontaneously, means the energy level should be high. So then it can, the cathode chemical potential is represented by mu c, and its energy level should be low because it is in the acceptor level. So if it is in the below energy only, this electron can come easily here. If the cathode is above, it cannot go spontaneously. So that's why this is the one of the requirement. So the chemical potential of anode and cathode, if it is the difference is more voltage or more EMF is expected. So therefore, in any battery, when you're designing, you should choose that the chemical potential of anode should be at higher level and the chemical potential of cathode should be at lower level, because it is empty. It is whole. Whole means what? It can accept electron. So there is no electron here. It's empty level. So this is about anode and cathode, which defines the voltage. However, when you are choosing the anode and cathode, you can choose the anode and cathode with wide window difference. But unfortunately, we don't have the electrolyte that can sustain. So here the electrolyte is also playing a vital role when you are deciding the anode and cathode voltages, the chemistry. Here you see that the electrolyte is directly contact with both anode and cathode. The electrolyte is should be chemically inert. Okay, electrolyte should not react, right? Electrolyte should not react with anode or cathode. It should acts as a medium for the lithium ion to move from anode to cathode, isn't it? So therefore, when you choose the electrolyte is an organic solvent, right? The electronic energy levels of the electrolyte are represented by WOMO and LUMO. WOMO and LUMO. WOMO means highest occupied molecular orbital. Means this is the energy level where electrons are present in this electrolyte. It may be ethyl carbonate or methyl carbonate or ethyl methyl carbonate. LUMO means lowest unoccupied molecular orbitals. Means they should have empty energy levels. Empty energy levels. Okay. So one of the requirement to choose the electrolyte is that the LUMO level should be higher than this, higher than the chemical potential of anode. The chemical potential level, the energy level of the anode, it should be above. And the energy level of the WOMO of electrolyte should be below the energy level of the cathode, because you can see here this WOMO of the electrolyte and LUMO of the electrolyte should be wide. It should be above and below the cathode, and the LUMO should be above the anode. WOMO should be below the cathode. Suppose, in case if you choose the electrolyte where the LUMO is below this anode energy level, then what happens? The electron present in the anode can directly enter into, can directly react with the electrolyte, and it undergoes electrolytic reduction reaction. Reaction takes place. Means the lithium is directly reacting with electrolyte. So this is called during SEI formation, solid electrolyte interface formation. Initially, some amount of lithium undergo reaction. Okay, so and forms a film. So therefore, we want the electron of anode should come to cathode. Then only get energy, electrical energy. So therefore, the LUMO level, energy level should be higher than the anode. That is one thing. Another thing, the WOMO, highest occupied molecular orbital, means the energy level which is containing electron should be below the cathode. Okay, what happens? Suppose if it is above the cathode, like this, above the cathode, if it is here, then the electrolyte energy level, the electron enters into the cathode. Okay, because cathode wants that electron because it is empty. Cathode energy level is empty. Cathode is always willing to take electron. So it will take electron from the WOMO of electrolyte itself. As a result, the electrolyte will undergo oxidation. So if you do not choose the electrolyte with the wide WOMO-LUMO, so what happens? So the anode will oxidize at LUMO level. At WOMO level, the electrolyte will undergo oxidation. So it can undergo both oxidation and reduction. So finally, that electrolyte may decompose, or you cannot, that battery will not work. Okay. So voltage, it's not only depending on the chemical potential of anode and cathode, it also depends on WOMO-LUMO level of that electrolyte. So with this background, let us understand the cell voltage, the open circuit voltage. So open circuit voltage is the voltage of the cell which is not under any load. Okay. It is the E cathode and E anode. For example, it is the difference between E of LiCO2 minus E of graphite, C6. So initially the voltage is 0 because it depends on the lithium ion concentration. When we start charging, the lithium ion are pushed to graphite. Okay. So it will become a voltage of Li1 minus X COO2. Of course, cobalt, there are two cobalt. Let us not show here, and LiX C6, right? So here this is negative, this is becoming negative, and this is becoming positive. So therefore, this is becoming negative. Initially, the voltage of graphite, so this is C6 and this is LiCO2. Initial voltages of this anode and cathode. Upon removing X lithium, upon pushing lithium from lithium cobalt oxide to graphite, we are moving from 0.2 moles to 0.4, 0.6, and 0.8. You can see that it is because of increasing the negative charge, the potential is becoming more negative for the graphite, and for the anode, it is becoming positive, the potential increases. So because of the positive, so the difference also, more positive, more negative, and the difference also increases. So the difference between these two is that E cathode minus E anode, so that also increases here. Okay, this is the cell voltage, the difference between these two. So of course, why there is a sudden dip, why there is a sudden increase, all those things will be discussed later. So this is about the voltage of the battery cell EMF. Based on if any material voltage is below 2 or 1.9, they're all considered as anode. Even lithium titanium oxide, LTO, graphite, lithium titanium oxide is around 1.6, 1.4, and graphite is around 0.6. Okay, and silicon carbon composite, lithium metal, silicon metal, so their potential is below 1.9 volt. They're all used as anode in lithium ion battery chemistry, but only the graphite and LTO are currently being commercialized as an anode. And any material, if it shows the voltage above 1.2 or above 2 with respect to the lithium as a reference electrode, they are considered as a cathode material. So LMO, lithium manganese oxide, metal oxides, this is a lithium cobalt oxide, LFP, and NMC. You can see here LFP is around 3.2 and NMC is slightly higher. Okay, so then now the current technology, the future technology is the sulfur battery and the air battery. So the chemistry is very important. So the anode should have very high capacity. High capacity means it can store more lithium ion and low voltage. Cathode should have high capacity, means it should store high lithium and high voltage, and electrolyte should be large stability window. Okay, all other materials should be stable. So all these components matters a lot when you're designing the battery with respect to high voltage. So next, another important property, that is the capacity of the battery. So capacity of the battery is represented by Ah, ampere hour. So it represents how much lithium that is being stored in anode and cathode. So we know that the lithium is actually the amount of lithium is equal to the amount of the charge, that is electron. So let us understand, with respect to the number of moles of electrons or current that is being discharged or utilized for charging, we can calculate the capacity of the battery. So we know that the charge of one electron is 1.6 into 10 power minus 19 coulombs. We all know that. So if you take 1 mole of electron, 1 mole means Avogadro number. So for 1 mole of electrons, this is Avogadro number, 6.023 10 power 23 into 1.602 in 10 power minus 19 coulomb. It will be 96,485 coulomb per mole. It is called 1 farad. Okay, so 1 farad is equal to 96,500 coulomb per mole, charge of 1 mole of electron. 1 mole. So 1 electron is this much. 1 mole is 96,485 coulombs. Okay, so let us define the ampere. So we want Ah, right? Capacity unit is Ah. Let us define ampere first. So we know that ampere is equal to coulomb per second, right? Coulomb per second. So we have coulomb here and we have ampere here. So first define, we want Ah. So S is here. Take that second to here. So ampere second is equal to 1 coulomb. Ampere second is equal to 1 coulomb. Convert that second into hour. So ampere second, it can be, so 1 by 60 into 60. So this will be 1 second. Okay. So this is equal to coulomb. So this is 1 Ah is equal to 3600 coulombs. This will be 1 Ah means 3600 coulomb. Okay, so let us calculate for 96,485 coulombs. That is 1 mole. 1 mole. So 1 mole is equal to, it is about 96,485 divided by 3600. Okay, so this will be is equal to 26.8 Ah. So 26.8 Ah. So 1 mole of lithium means 26.8 Ah. Means Avogadro number of lithium ions are being stored. 6.0 to the 10 power 23 lithium ions are being stored. That gives the capacity of 26.8 Ah. Okay, so you can calculate, if you know any Ah, you can calculate how much amount of lithium is stored, chargeable and dischargeable lithium. So that is theoretical capacity, but the capacity is with respect to compare the battery chemistries of all the other cathode materials. We always calculate for per gram of that X and Y, per gram of lithium cobalt oxide and per gram of NMC. So that is called specific capacity. That is Ah per gram. So this is the formula used for that. NF by 3.6, that is 3600. So this is the number of moles of the charge and Ah per gram. So let me compare the battery capacity, the specific capacities of various battery chemistries. So lithium cobalt oxide, let me take that as an example. LiCOO2, its molecular mass is 97.87 gram, means that is actually 1 mole. So 1 mole, which can give 1 mole of lithium if you extract completely. If you extract completely from the lithium cobalt oxide, you can extract 1 mole. So 1 mole means how much? 26.8 Ah. Okay, so that is for 1 mole. That is for this is theoretical capacity, but the practical capacity is this is for 97.87 gram can give 26.8 Ah. Okay, but you should calculate for per gram. Okay, so for 1 gram, 1 gram is 26.8 Ah divided by 97.87 gram. So this will become 0.27 Ah. This will be 0.274 Ah per gram. So that is converted to milli Ah. That is 274 milli Ah per gram. So this is a theoretical capacity of this. More the theoretical capacity means we can expect more lithium can be stored and charged. But practically there it is not possible to extract complete lithium because there are some structural stability issues. So therefore we can expect only 148 practically we can achieve. So you can calculate 148 milliampere Ah. You can how much lithium you can extract from lithium, how much lithium is remained in that matrix. That can be calculated, and this is the voltage with respect to lithium for that LiCO2 3.8 volts. Then NMC, this is a nickel manganese cobalt oxide. It is also modified COO2 where they have doped nickel and manganese for about equal percent, 1:1:1, and its molecular weight is this one. And 26.8 Ah divided by 94.54, you get 0.280 Ah per gram. 280. They have increased by doping nickel and manganese. They have increased the capacity of the LiCO2, that is NMC, by converting that to 80. But practically they could able to get 170, means instead of 148 they have increased to 170. Okay, so like that the battery capacity of all the other materials are listed here. You can see that LFP, why people are behind LFP means you can see that its practical theoretical capacity is 170, practical is also almost same, 165, means almost 90 to 95% of the lithium it is involved in charging and discharging, right? So but in case of NMC, almost 50% of the lithium is remained in that matrix, it cannot remove. Similarly LMO battery, but you can see large difference in theoretical and practical capacity. LTO is 175, theoretical and practical is 100. And the graphite, you see why graphite is largely used as anode in all the battery chemistries is because of its 372 milliampere hour theoretical capacity. But the practical capacity is around 360, almost same. That's why the graphite is being preferred. So overall, this battery capacity, specific capacity, that is milliampere hour per gram, represents how much lithium can be stored and in both anode and cathode. So that again depends. It increase, depends on the voltage. More the capacity, more is the voltage difference. So then we have power density. So power is watt per kg or watt per liter. So power depends on the voltage and the current, and the energy depends on the Ah. So power depends on voltage, and the energy depends on the capacity. So energy is the Ah into voltage, cell voltage and Ah. So energy density is with respect to the weight. So the weight should be less for the given battery, and the energy stored should be very high. Energy is the product of voltage and the capacity Ah. So power density and energy densities are very important key characteristics of the battery. So all these things, I'll just skip this. Next, come to the important characteristics of the battery, that is over potential. So over potential, I have discussed about in the Nernst equation, the voltage. So voltage that we mentioned, actually the LiCO2 is expected is 4.1 volt, but practically we can get only 3.8 or 3.7. That much of voltage will be lost during discharging, or while charging, that much extra voltage you should apply. So that is called over voltage. It's an additional voltage beyond the equilibrium potential. It's required to drive certain electrochemical reactions at the electrode surface. So it's extra voltage is required to drive that anodic charging or discharging. It's actually the difference between the actual potential applied versus minus the equilibrium potential to drive the oxidation and reduction reaction. So it is represented by the eta n. Eta n is E minus E, this one. So let us consider the reaction This is actually oxidized species can accept electron and can undergo reduction reduced species. So this is the forward reaction. The Kf is the forward reaction rate constant, and Kb is the backward rate constant. If the Kf is high, the forward reaction is favored, then the reduction reaction takes place. Means oxidized species can accept electron and can become reduced species. So that can be, once it attains the equilibrium, the potential measured when no reaction is happening, that is called equilibrium reaction. Okay, where there is no axial oxidation or axial reduction taking place, that is called equilibrium potential. But if you want to push the reaction this side or the reaction this side, you have to disturb this equilibrium. That is by applying extra voltage, negative voltage or positive voltage. If you apply extra voltage, okay, if E is greater than equilibrium potential, okay, if you apply the more voltage, then if E is greater than E equilibrium potential, then the reduced species are getting converted to oxidized species by losing the electron. So this reaction is dominated. This reaction, the backward reaction, takes place. As a result of that, anode reaction, the oxidation reaction takes place. That is called anodic polarization. So for anodic polarization, the eta is more because eta is greater than 0 because the applied potential is greater than equilibrium potential. Similarly, if you apply the below voltage than equilibrium potential, then the forward reaction takes place. Oxidized species can accept electron and getting reduced. So the reduction reaction take place. As a result, we call it as a cathodic polarization, and the potential, the eta, the over potential will be negative. So overall, the cell voltage is the equilibrium potential minus the over potential. So over potential actually depends on various factors. It is actually sum of the activation over potential, ohmic over potential, and concentration over potential, and plus also some other contacts and others. Okay, so E equilibrium is the open circuit cell voltage at that SOC, and I'm going to cover in detail about charge transfer, that is activation over potential. So this is governed by Butler-Volmer equation, and this is the ohmic drop. It is because of the electrolyte separator, current collectors, and contacts. And we have one more contributing factor for the over potential, that is concentration or mass transport over potential. That is ion solid diffusion limits. So when you are discharging a cell or a battery, actually initially when you charge the battery, this will be the initial voltage V1. Okay, when you're discharging the battery, so the voltage drops slowly, gradually. There is a steep decrease in the voltage upon discharging. It is because of some amount of the voltage, whatever the energy is consumed to drive other reactions. So not it is coming out as electrical energy. So it is because of it is due to the sum of the IR loss, that is called ohmic over potential, the first one, and it also some of the voltage is utilized for the charge transfer, means the electron transfer between the electrode and electrolyte, and some extra voltage is consumed for that mass transfer, means lithium ion movement from the anode to cathode in the electrolyte. So I'm going to discuss these two, the activation polarization or the concentration polarization. So the cell voltage under the load is sum of the over potential is sum of these three. So if more over potential, then the loss is more. This is the loss is more. If more loss, then the output, the capacity is also less. The output capacity. Initially, there is a more output capacity because the voltage is high. Upon upon discharging, since the voltage drops, the capacity also drops. That is AH. If AH drops, the power and density also, the energy density also drops, because energy density is the product of AH and voltage. So it's mainly because of this charge transfer and the concentration polarization, whatever this charge transfer that is the phenomena which takes place between the electrode surface and the electrolyte, and the mass transfer that is in the medium, that is electrolyte. So now to understand that, first let us understand the electrode and electrolyte interface. So that is defined based on the three models: Helmholtz model, Guy-Chapman model, and Stern model. Okay, so in this diagram, let us assume that the yellow color one is the electrode. So this is the electrode, positively charged electrode. So it attracts negative ions from the electrolyte. So according to Helmholtz, so the electrode and electrolyte interface, the charge separation takes place. If the electrode is positively charged, then to balance that charge, the negative ions from the electrolyte, they come and accumulate. And as a result, electrical double layer is formed. Okay, so the lithium ion transfer and SAA formation and interface impedance, all of in the battery depends on this the double layer formation. Okay, so in the Helmholtz model, as per Helmholtz model, it's a compact layer. Specifically, the lithium ions or the cations or anions are absorbed next to that surface. So you can see here the electrode is positively charged. We have negative ions next to that, and it acts as a perfect capacitor. So ideal capacitor. Okay. If the opposite charge, if the electrode is negatively charged, then we will have lithium ions, the positive ions next to that surface. But this model actually, it is not considering the size of the ions, the hydration of the ions, and also the diffusion and the migration concept. So therefore, they have proposed one more model that is called Guy-Chapman model. So this is the next model. According to Guy-Chapman's model, the ions are distributed. You can see this is the positive layer. Then the ions, the negative ions are distributed gradually in the electrolyte. So then the potential decays exponentially from the electrode. It is because of the distribution of the charges. This Guy-Chapman has considered both the solvated ions also. This is the solvated cations, and we have the anions next to that. It's not like perfect layer, not like a perfect capacitor distribution. They've also considered the motion and also the ions which are experiencing the repulsion and attraction, when they're accumulating on the surface of the electrode. With respect to lithium ion battery, this context, the mobile, the solvated lithium ion here and PF6 ions in the liquid electrolyte is considered in Guy-Chapman. However, in the Helmholtz model, it is ignored. So next, there is one more model, the realistic, which is actually close to the lithium-ion battery. That is actually Stern model, which combines both the Helmholtz and Guy-Chapman. So initially, there is a formation of the positive and negative ions. That is the first like a capacitor without the desolvated ions accumulate. This is called inner Helmholtz plane. Then we have solvated, another layer with the solvated ions. This is negative and positive. That is outer Helmholtz plane. Then we have the diffuse layer, that is extended ionic region. So this has covered all the three. This model is actually close to our lithium-ion battery technology. I'll just skip this. Okay. Let us understand the electrode reaction kinetics in LIB lithium-ion batteries. So this is the electrode. Let us assume that this is the electrode, and we have oxidized species means Li plus. So electron. Li. So lithium is reduced, Li plus ion is oxidized, and we have rate constant for the forward reaction and rate constant for backward reaction. So initially the ions, the oxidized species which are present, oxidized species means Li plus, which are of course solvated. So they're solvated with some organic solvents, and their concentration is different, and they started moving. When you make this as negatively charged, so obviously the lithium ions are started moving. So while moving, they have to experience the repulsion from other negative ions. Positive ions will be in the solution. Negative, positive, they have to overcome that, right? So then they come near to the surface. So surface means near to the surface of the electrode. So then that lithium ion, then it will undergo absorption. It will absorb on lithium. So once it will absorb on the surface, then it will accept electron and undergo charge transfer reaction. So here the charge transfer, lithium undergo reduction. So the overall the process which follows two phenomena. One is the mass transfer, that is in the solution. Another one is a charge transfer. So this charge transfer is governed by the Butler-Volmer equation. So which represents the rate at which the reduction and oxidation reaction is taking place. Means that electron transfer. Okay. Mass transfer is governed by Fick's law and Nernst-Planck equations. So that will tell us about how fast that ionic mass, that lithium ions are moving between the electrode. So mainly the electrode reaction, whatever the battery, the charging and discharging, that over potential, all those things are depending on these two phenomena, mass transfer and charge transfer. So similarly, once it is getting reduced, so it then it will undergo the same reaction. During charging this happens, during discharging this reaction happens, but all of them will follow the resistances in the solution and also near the surface of the electrode. So actually that over potential, as I mentioned, it's a sum of the mass transfer over potential, charge transfer over potential, and ohmic over potential. The mass transfer is over potential is actually extra voltage required to drive. For example, if the lithium ion is accumulated here, there will be a more lithium. There will be difference in the there will be difference in the lithium ion concentration in the bulk and also in the near the surface. So that difference leads to the concentration polarization. So that requires extra voltage to drive to make that concentration to be uniform during charging and discharging. So this is called mass transfer over potential. So this is because of slow transport of lithium ions through electrolyte and also the solution. Then the charge transfer, that is activation over potential. It is actually the potential needed to overcome the energy barrier for the electron from the surface to that lithium. This is actually a phenomena which takes place in the interface between the electrode and electrolyte. So this is because of slow interfacial reaction kinetics during lithium ion intercalation and deintercalation. So ohmic over potential, it is a voltage drop. It's mainly due to the resistance to current flow. It is because of the electrolyte, and we have other components like separator, the electrolyte viscosity and electrolyte nature, the separator thickness, separator porosity, the electrodes are getting corroded, and if there is no contact. So all those things also add up some resistance. So that again demands more potential, that is called over potential. Okay, so let us briefly explain that concentration polarization. Concentration polarization, which contributes to the mass transfer over potential. You can see here, if the lithium ion constant, this is the electrode, lithium metal and the lithium electrolyte. This is at equilibrium. This is the case one. At equilibrium means E is equal to equilibrium. The concentration of lithium on the surface and the concentration of lithium in the bulk. So this is the red one is the bulk lithium ion. If they are same, so this is at equilibrium now. No reaction is happening. No charge transfer and no mass transfer. So E is equal to equilibrium. So then over potential is 0 because no reaction is happening. Current is also 0. So here the rate of forward reaction is equal to rate of backward reaction. At equilibrium, no net reaction. Okay. Since the concentration is same, there is no polarization here. The concentration throughout the whatever that electrolyte is same. But let us consider the second case. If applied potential is greater than equilibrium potential, if the applied potential is greater than equilibrium potential, then oxidation reaction take place. The lithium metal from the electrode undergo oxidation reaction. So you can see it is releasing electron outside, and then that lithium becomes lithium ion. So where will that lithium ion goes? Obviously, it will go near to the solution, which is close to the electrolyte. So therefore, so because of that, this one, the surface, the lithium ion on the surface of the electrode concentration increases, and then it is greater than the bulk concentration. Here, the bulk concentration is less than the lithium ion concentration near the surface. So this actually, this leads to the oxidation reaction. When the applied potential is greater than equilibrium, the over potential is positive, increases, and the current also increases. Here, the forward reaction is slower than the backward reaction, as I mentioned in my previous explanation. So here, the over potential is positive based on the Nernst equation. Similarly, if okay, if the applied potential is less than equilibrium potential, means you are pushing that reduction reactions to take place. Okay, reduction reaction means you are just applying the electron to the applied potential. Okay, here this will become electron rich. Then the ions which are next to the surface, the lithium ions, enter into that electrode, and by accepting that electron, and they become metallic lithium. Okay, so they get accumulated, they get deposited. This is called lithium plating. As a result of lithium plating, so the lithium ion concentration near the surface of the electrode decreases, and as a result, there is a difference between the bulk lithium ion concentration and surface lithium ion concentration, that again leads to concentration polarization. So to make it uniform, again you require some more potential, that is called mass transfer over potential. So this will be again the over potential is negative because it is undergoing a reduction reaction, and the forward reaction is greater than backward reaction. So all this, the three types of, what is that, three cases, the equilibrium, negative and positive potential, over potential, all those things, over potential is governed by the equation that is called Nernst-Planck equation. So the mass transfer process, it is due to the concentration difference in the electrolyte is equal to the flux, the current, the flux of the ionic species. The flux is the number of ions of the lithium ions per mole, number of moles of lithium ions per centimeter square on the surface of the electrode per second, is equal to, it depends on three parameters. One is it depends on the diffusion of the lithium ions, and migration of the lithium ions, and convection of the lithium ions. Three phenomena are involved in order to make it uniform. So diffusion is with respect to, is equal to minus di, this diffusion coefficient, into concentration difference. dc, I means ith species, difference in the concentration at a distance x. X is the distance from the electrode and a solution, and dx is the distance between that ion and the electrode interface. So this is the diffusion concept, and minus zi is the charge of the number of the ion. F is the Faraday constant, R is the gas constant, T is the temperature, and di is the diffusion constant, and C is the local ion concentration, that is mole per liter, and d pi is with respect to voltage. Migration with respect to difference in the voltage in the solution. So because of difference in the concentration, there is a formation of less concentrated ions one side and more concentrated ions in the other side, that leads to the difference in the voltage. That is called electrical potential. So migration is because of the electrical potential difference within the electrolyte, and diffusion is because of the difference in the concentration. So overall, this concentration polarization is actually depending on these three. In battery, it is because of it is related to the bulk fluid velocity. So since our battery liquid is not moving liquid, except the redox flow battery, so in most of the batteries, this is neglected. So this is taken as zero. So the main contributing factors are migration and diffusion. That depends on the voltage that is arised, the voltage difference, and also the concentration difference in the electrolyte. So the ionic flux is of the lithium ion is mainly due to the diffusion. Migration, convection is neglected in our cell. So in diffusion means ions moves from high to low concentration. So the It controls lithium ion supply in electrolyte and electrode. Migration ions moves due to electrical field. So because of plus 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 and minus minus in the solution, there is an electric field being created inside that electrolyte. So that requires more potentials to overcome that barrier. This drives the lithium ion under current flow. So what it tells us, if lithium ion diffusion is slow in the electrolyte, means what? Very high mass transfer over potential. Okay, so it explains the voltage dip. So the voltage decreases in the battery at high C rates. So from the, if you find that there is a voltage dip in the battery at high C rates, it is because of lithium ion diffusion is too slow. So that is what we should understand. Then migration limited by low conductivity. So it causes ohmic losses that depends on the nature of the electrolyte. Then concentration gradients near electrodes. So that is because of the difference in the ionic concentration. So that leads to if more ion concentration is present, then it leads to lithium plating during the fast charging. Fast charging means more electrons you push, so then more lithium is being it started plating. That leads to dendrite growth and all, and it may also spoil SEI formation. So overall, the understanding is the Nernst-Planck equation helps us to quantify the ion transport and understand power limitations in real cells. Okay, I'll just skip this. Okay. So this mass transfer over potential, the diffusion coefficient Di, which represents the speed of lithium ion movement. This can be determined by using GITT, galvanostatic intermittent titration technique, and PITT, potentiostatic, and EIS by using that Warburg tail. So that is so this will be covered in the unit 3 of our the battery materials characterization on digital twinning course. So we have covered almost 3 to 4 hours of discussion about EIS, where we use the technique to find the diffusion coefficient. Similarly, the sigma, the ionic conductivity. So we use AC impedance measurements, and the transport number we use Bruce Vincent method. This is also being discussed in one of my video in detail. All these techniques are discussed and their significance to find out all these parameters. ES is actually widely used to measure charge transfer and ohmic resistance. So far I've discussed about the concentration. This I have finished the concentration polarization. Next I'm going to cover with activation polarization. Okay, so far I have covered this mass transfer from here to here. Then now I'll be focusing on this portion. So where the charge transfer, that is Butler-Volmer equation, where how fast that electron is being transferred to lithium means undergoing reduction reaction, or how fast the oxidation reaction is happening, intercalation and deintercalation. So the Butler-Volmer equation, which helps us to understand the electrode charge transfer kinetics. So it is equal to the current, the current that we are able to get or apply is equal to the exchange current density into e power minus alpha into f of eta. So this is actually the relation between the current and I and over voltage. It's a relation between the current and over voltage minus E into 1 minus alpha into F by N. So I have actually derived this equation in my recording in the course. There are two detailed, almost 2.5 hours discussion about this Butler-Volmer equation. How we get this equation, how do we get this anodic and cathodic, all those things are discussed in detail. If you take that course, you will come to know how the Butler equation in various different cases and all is being discussed. And about alpha. So alpha is a transfer coefficient. It should be between 0 and 1. What is the meaning of alpha? That is a symmetry factor. What happen? When will it be symmetry, and when in which case it will be asymmetric? So what happens if it is 0 to 1 or 0 to 0.5 or above 0.5? What does it signify? All those things I have explained in that recording. So here I'll just briefly cover how BV equation is used to understand charge transfer kinetics. So F is actually NF into by RT. N is 1 for lithium. So here next the eta. So that over potential is applied potential minus the equilibrium potential that I have discussed. The physical meaning of this Butler-Oemer equation is which describes how the current density I varies with over potential during the charging or discharging in case of battery. It links both the thermodynamics and the kinetics. Kinetics means the rate at which the electrons are being transferred at the electrode and electrolyte interface. Actually, it has two components. One is the cathodic and this is the anodic. This is cathodic and anodic, both oxidation and reduction process. So at equilibrium, so eta is equal to 0. So current is equal to 0. So both forward and backward reactions are same. The context of lithium-ion battery, the anode during discharging, this is the discharging reaction of the electrons. So the electron and ion transfer transfer from graphite surface. So how fast that the lithium ion are coming out from that graphite, and how fast that lithium ion are coming out from that graphite decides the charge transfer, the rate of the reactions. That can be understood by Butler-Oemer equation. So where we can apply there, and also similarly the cathode, the lithium ion intercalation, deintercalation at the cathode electrode. Overall, the reaction rate at each electrodes follows Butler-Oemer equation, which covers both charge and discharge kinetics and the charge transfer over potential. So at low over potential for about less than 10 to 20 millivolt, it will be linear zone. This expression, the Butler-Oemer equation, it simplifies as the current density is equal to exchange current density into F into eta. So we know that then if you rearrange that, F is equal to NF by RT, NF by RT. So NF by RT, if you substitute that, so then eta is equal to V is equal to IR, right? So V is equal to IR. So eta is equal to I into R CT. If you substitute that, you get this expression. So RCT is equal to 1 by NF. So if this is eta is equal to I naught into F. Okay, so then I by F is this one. You get this expression. RCT is equal to RT by NF into I naught. So small signal reason, this can be our charge transfer resistance can be extracted from that EIS impedance measurement. Then at high over potential above 50 to 100 millivolts, the only one of the exponential terms, one exponential term dominates, whether it's anodic or cathodic. It depends on which the potential that is being applied. If one potential means, you can easily reduce this expression. You can take log, and it becomes eta is equal to A plus B into log I, logarithmic I. So it will be is equal to Y is equal to mx plus C plus mx. Okay, so where m is the slope, so b is the slope of, that is also called Tuffel slope. It is 2.303 RT by ANF. If you rearrange this, and if you can simplify that expression by taking log, you will get this. So where I naught determines intrinsic reaction rate. So here this alpha term, the alpha term playing a vital role in Butler-Oemer equation. So it is also called charge transfer coefficient. Let us understand the significance of this. So alpha represents how the activation energy barrier is split between anodic and cathodic directions. So it is when you apply the voltage, means you are applying the energy, that is the free energy. You can disturb the equilibrium by applying the positive voltage or negative voltage, means delta G is equal to NFE. Okay, so that drives whether the anodic reaction should take place or cathodic reaction takes place. So it's typically between 0.3 and 0.7 in lithium-ion batteries. So higher alpha means faster current rise with over potential. So lower charge transfer over potential. So and better kinetics. So higher alpha value is the better for charge transfer kinetics. So changes in alpha indicate surface film formation. and a CI growth. Everything is actually, it is interface, this electrode interface phenomena. It depends on solid electrode interface degradation at electrode and electrolyte interfaces. It's measured from Tafel slope, that alpha. As I alpha, this can be obtained from this B equation, Tafel slope B. This alpha is equal to 2.3 RT by BNF. So this value will tell if it is more, means the kinetics is good. So charge transfer is easy. So in this equation, the current density, higher current density means the faster kinetics, low over potential. It should be good. So this is a good one for a good battery. Alpha charge transfer symmetry factor, it should be easily between 0.3 and 0.7, influences the Tafel slope. The charge transfer resistance inversely related to I naught, and the activation over potential, the overall energy barrier for the reaction. So EA is the activation energy. So that depends on this activation over potential. It reflects the intrinsic reactivity or solid electrolyte interface effect. So how do you measure these BV parameters in lithium ion batteries? So the charge transfer resistance that I have mentioned. So it is used by using EAS, electrochemical impedance spectroscopy. So where we get that Nyquist mid circle, that mid frequency. So that will give you the RCT, and the current exchange current density from the Tafel analysis or DC polarization, and also that I naught can also be determined from cyclic voltammetry, etc. So overall, I'm just now with this, I'm summarizing my discussion today. So in this bootcamp talk, we have just given the flavor, just 1% of what we have discussed actually in the main course. So that Butler-Omer equation itself have discussed about 2 to 3 hours. Um, so it is just a flavor teaser of the film, I can say. To summarize that, lithium-ion battery, the controlled lithium within the solution and the electron flow outside between the cathode and anode it is governed by various principles, and for that you need to understand the basic concepts of electrochemistry. So therefore the foundations are very important. The voltage from electrode potential difference, which defined by redox chemistry, that is by Nernst equation, which explains the variation of voltage, that is again depends on the concentration of lithium, exchangeable lithium, not all the lithium, exchangeable lithium ion in the anode and cathode, that is related to the state of charge. So, and we have discussed about ore potential. So the ohmic potential, this resistance loss, this is actually physical phenomena, and the charge transfer, Butler-Omer equation, and mass transfer, that is with respect to the lithium ion moment concentration and the voltage. This is the Nernst-Planck. It's based on Nernst-Planck equation, and then we have also understood the double layer, the Helmholtz layer, Guy-Chapman and Stern layer, which controls the charge separation and also the reaction initiation. And we have discussed about Butler-Ulmer kinetics, how the current and ore potential are interlinked, and what are the key terms, that is exchange current density, transfer coefficient, and charge transfer resistance. So high current density, low RCT means fast kinetics, low polarization, and better rate performance. So hope you guys have got some information about the electrochemistry, the importance of the electrochemistry, not to understand the lithium-ion battery for the development and then for testing, especially for the simulation. It's very important because you are going to use a lot of all these terms: the RCT, transfer coefficient, the current density, the voltage, capacity, and all. So thank you. I'll just pause a minute. You guys, if anybody has any questions, the session is open to question now. Hello.
If you have any questions, you can leave it in the chat box. We'll take those questions.
Even if there are any
So we have
questions
a
you come
question.
across later, you can email me. You can share my you can share to Vinayak so that I can address them.
So we have two questions in the
Yes,
chat box. What is your view on solid state batteries?
solid state battery is upcoming battery. Since you have seen now that so now I discussed mass transfer over potential, that is because of lithium ion diffusion. That completely the Butler-Omer equation, it will be changed for solid state chemistry. The EIS impedance spectroscopy, it will be different. In terms of safety, solid state battery is better. That's why people are moving towards shifting to solid state, because here we are using organic electrolytes. They are actually flammable, and they react with lithium, as I showed you in LUMO and WOMO levels. They actually react. That is because of that. In solid state battery can go for high voltage cathodes. The main demerit of the challenging task for the solid state battery is the electrolyte, the solid electrolyte that is being used between the anode and cathode, where that the lithium ion diffusion DLI plus I have discussed now in that Nernst Planck equation. So that is actually very less, because the lithium ion has to percolate in the solid matrix only. But in this battery, the lithium ion can swim easily in the liquid electrolyte compared to solid. So people are actually doing a lot of research in developing efficient solid electrolyte. They're able to realize that highly conducting the electrolyte, then solid state is a very good choice. Hope I have answered questions. Is there any other question?
How to calculate captive capacitive and diffusive capacity, the contribution from the overall capacity? What is the significance?
Just repeat that question again.
Yes, sir. How to calculate capacitive and diffusive capacity contributions from the overall capacity? What is the significance? You can check in the chat box, sir, if you want.
I have explained about the capacity is actually theoretical capacity is it can be easily calculated actually based on the molecular formula. That is 26.8 Ah. If it is releasing 1 mole of lithium or 1 mole of electron, divide by its molecular mass, you will get theoretical capacity. But achieving that, it's not easy, because as I mentioned, in the lithium cobalt oxide, it is about 274 milliampere hour per gram theoretically, but practically you can get only 140. That is actually diffusive capacity. Means diffusible means the amount of lithium ion you can extract by charging from cathode to anode, amount of lithium that you can push without spoiling the crystal structure. That is actually the practical capacity that you can say diffusive. That theoretical is one that we calculate. So that again depends on the crystal structure that have covered in some of the videos in the unit module 2, have exclusively discussed about the crystal structures of lithium cobalt oxide, why the practical capacity is less for that. There is a liberation of oxygen if you remove more lithium, and there is a collapse of crystal structure, and as a result it will fail to get more cycle life, and it also leads to degradation. So obviously that capacity is calculated based on that SOC, the state of charge. So there are various techniques and various formulas that has been discussed in detail in the course. And you will also be studying that module 3 will be on electrochemical characterization, where I have covered all the GITT and the cyclic voltammetry and chronoamperometry and electrochemical impedance spectroscopy. So in that module, I have explained how to know how the techniques are being used to calculate all this.
So what is the main function of the separator?
Separator actually it's a chemically inert and electrically inert. It is since anode is negative, right? So anode chemical potential is high, as I showed you in that graph. It's chemically highly reactive, electron rich, negatively charged. When you charge, anode is highly negative because of lithium, and cathode is lithium deficient and positive. When you have negative and highly negative and highly positive, if they come in contact, right, directly, obviously there will be a short circuit. So we want that electron to come out through wire, not internally. If there is no separator, if anode and cathode, if they touch each other, then they're inside the battery only, they will exchange electron and may undergo chemical reaction. So it will spoil the battery. So there is no, so you won't get current. So therefore, to prevent the short circuit between the anode and cathode, we place the separator. Separator is an inert polymeric material which is porous in nature. Porous means it's like a sponge and oily porosity. It will allow only the ions, the lithium ions between the anode and cathode, not electrons. It is electronically insulator, ionically conductor. So that is the specialty of the separator. So it will like a curtain which covers both anode and separates anode and cathode.
So next question, what is the main difference between electric double layer and an SEI layer? Is that both exist at the same time in the battery?
Electrical double layer is a phenomena that takes place during charging and discharging. They may disappear and appear. It is just an accumulation of ions. Okay. When you charge, when you make electrode positive, and that positive electrode attracts negative ions and they absorb. When you start discharging, when you change the polarity of the electrode, if it is now positive, it has attracted negative ions. You change the polarity, if you make negative, that ions detaches. It's not permanent. So that is about electrical double layer. That is a temporary. Okay. But SEI is a solid electrolyte interface. It's a thin film that is actually being created intentionally on the surface of anode to prevent the lithium plating and also the dendrite formation. The lithium, that SEI is a porous thin film. It's not like a double layer. Thin film made up of some inorganic lithium salts, lithium ethylene dicarbonate, and mixture of various components. A thin coating is formed, and that should be permanent. That is very important because the role of SEI is the lithium. When we charge a battery, lithium moves from cathode to anode and enters inside the graphite, right? So if you charge more lithium enters and it may come out. Once it comes out, no, the lithium starts reacting with the electrolyte. As I showed you, lithium is highly metallic. After reducing, it starts reacting with electrolyte and liberates gases, and it may lead to lithium plating or dendrite formation, and it start growing and it may come and hit that separator and come out from the separator and it may connect with a cathode, and that may lead to short circuit. So to prevent that lithium ion to come out once it enters inside the graphite, so there is a film that is being created. That is after after constructing the battery, they fill the electrolyte, and then before then they carefully charge the battery with the slow, slow C rate, low C rate only. They charge the battery and discharge the battery several times, and then slowly the thin film is being formed. So that is actually very important stage that is called battery conditioning or battery formation. So that I have discussed in SCA. About SCA I have covered almost 1.5 hour information in my main course. So there you will get a lot of information about that SCA. Of course, that double layer and SCA, they are completely different. On the surface of SCA, you can expect the double layer formation. So that is observed in charge transfer. So that is charge transfer is because of RCT in the EAS. In the EAS, if you go to imaginary impedance, that is because of the formation of capacitive behavior. So wherever you get capacitive behavior, it's because of double layer, electrical double layer. Yes, I think. Okay, next question. Hope I have answered your question. Vinayak, is there any other questions?
Yes, sir. One last question. What is the physical meaning of polarization of electrode? Is battery polarizable? Hard supercap is not polarizable. Third supercap is not polarizable.
Polarization is basically just imagine watching a movie. Okay, so when the movie starts, till interval, everybody is sitting quietly and uniformly distributed. Everybody is watching, and concentration, the distribution of the people in the auditorium is same, right? But once the interval comes, some people, they want to take bio break or they want to take some snacks. Everybody starts moving, randomly dispersing, and they get polarized, towards that exit door. This is the same kind of phenomena can be observed in the battery. That is because of the when you charge and discharge, the ion starts moving with respect to the respective electrodes. During that, there will be a non-uniform distribution in the charges inside the battery. That is called polarization. So the polarization leads to increase in the over potential. It's because of non-uniform distribution of the ions in case of concentration polarization, or in case of on the surface, it is because of non-uniform distribution of the electrons. Ions also accumulate non-uniformly on the surface of the electrode. So that is called polarization. Polarization alters the actual voltage. If all the ions accumulate uniformly on the electrode, then the potential will be same. If randomly accumulate, then you require more potential to redistribute. That is called over potential. Of course, that supercapacitor and battery, in both the cases, we can expect polarization. That again depends on the material and the electrode, the charging rate, discharging rate, all those things. A lot of parameters are actually playing a role here.
Okay, sir.
Okay,
That was
there
the
are no
last question.
questions.
Yes, sir.
No questions.
No, sir.
Okay.
Okay.
There are no questions. Thank you all for joining this weekend. If you have any questions, just write a mail to Vinayak. We can respond in the next meeting. So in the main course, you get more inputs about this. So with this, I'll be closing the session. Thank you, Hal. Happy weekend. Happy weekend. Thank you all.
Thank you, sir. Thank you for the session and thank you for this attending till here. Thank you.
Okay.
Have a great weekend. Thank you. Thank you, sir.
Thank you, Vinayak. Thank you, everyone. Bye bye.